My name is Chris, and I'm a postdoc and associated member of ML4Q, and you're listening to ML4Q&A, a show where members from the Matter and Light for Quantum Computer cluster answer questions about their work in the cluster, their research, and the future of quantum. In this episode, I'm talking to Beata Kardynal, member of ML4Q and group leader in Forschungszentrum Jülich and at RWTH Aachen. We talk about her career from electronic devices to using these devices to couple to single photons, her favorite materials, and how she didn't see a strong distinction between physics and engineering from the start. It is my pleasure today to have Beata Kardynal on the ML4Q&A podcast. Beata studied in Technical University of Wrocław, did her PhD in Cambridge, followed by a fellowship, postdocs in Arizona State University and Oxford, and worked at Toshiba, became an associate professor and group leader at Danish Technical University, and is now an associate professor at RWTH and a group leader in Jülich. So you see that she has a long career to talk about. So let's maybe start at the beginning. You have a master's degree in electronics, right?
That's correct, yes.
So this is not physics at the time, right?
Not physics at the time.
So you decided to do a physics PhD.
That is correct.
Cool. What got you from physics to electronics?
I think I wasn't brave enough to study physics at the time, considering career options. I thought I would see myself more in industry than a school teacher, which would be perhaps the most obvious career after physics. However, as time progressed at university, I loved saying that I loved my electronics curriculum. Part of the curriculum was device physics, and it convinced me that this is what I should specialize in, and it's what I did.
So did you get into the field excited by like the applications from the engineering standpoint, or more about the fundamental physics of electronics?
I actually, in choosing electronics rather than physics, I wouldn't say that I liked one or the other more. However, for me, electronics was a very cool and interesting physical realization of very mathematical abstract concepts. And I thought it was fascinating to start from something as abstract as mathematical equation and realize it on transistors put in some sequence and operated in a certain way.
I shouldn't talk about myself too much, but in my work on superconducting circuits, I also almost always find when we do analog design or microwave engineering that electrical engineers would probably do this better than me. Like it's true that there's some parts of engineering where people are certainly very well prepared for some of the aspects that physicists might not,
That's very true. So of course it was many years ago, but we had physics and mathematics was really the core of the degree. And when it comes to electromagnetism, solid-state physics in our case, linear algebra, I would say that we were really prepared to run quantum experiments as we do them today. So I often refer to some of my linear algebra scripts from university. Finding it a good text to look at.
I mean, it's also we recently when you do low noise electronics experiments, sometimes you have these fancy things that you can buy from Stanford Research Systems or whatever. But sometimes you can also solder together an op amp and
yes.
You can get a very good amplifier that is also low noise. So in a sense, a very solid knowledge of these things is very helpful for doing good physics experiments in electronics.
It is, and I do not think that there is such a big gap between engineering and physics. As everything in life, nothing is very digital. There is a spectrum of expertise you need. I think what makes a good experimental physicist is also a good grasp of engineering. If there even is such a distinction, I guess engineering is a sort of a little bit more targeted approach to problems rather than explorative. But we need that too if we want to set up experiments.
Yeah, I mean, especially in this quantum information field is a very interesting case where on the one hand you have kind of lofty quantum experiments, and on the other hand, really hardcore engineering challenges. I think it's almost it's kind of a special field in that way.
Yes.
So your PhD thesis, this was called Fabrication and Physics of Equilibrium Electron Tunneling Devices. Let me ask you first about how much fabrication you did, because maybe for young students that is something to when people hear fabrication, they think struggle.
Yes, it does not sound very fancy. I have not been, and I'm not very good in giving good titles, but it is also fair. Good 70-75% of my time was spent on preparing the devices that produced my data. This was maybe I should describe a bit what it is. So equilibrium tunneling is tunneling between two electron gases with no bias between them. So you can think of it as probing Fermi surface of one of the electron gas in a quantum well using the other electron gas. And I was given a task of realizing tunneling between one-dimensional and two-dimensional systems, and the question was how to do it. That was the title, and that was the advice from my supervisor: go off and bring me results. So of course, it is challenging to create electrical contacts to two quantum wells which are tunnel coupled. They are very close to each other. We had some new technology in the Cavendish laboratory to create independent contacts, but we also had still very primitive microelectronic facilities and clean rooms. So indeed, it was a struggle to create the device. To prepare the device, to isolate the 1D channels, to avoid having some artifacts. So my advice to any student is don't give up if your first and second year of PhD seems to be leading you nowhere. I'm sure you are learning, doing and progressing. It's just that very often the progress comes slowly, and then there is a big jump in performance. The other advice that I would give is probably not always listen to your supervisor when they tell you it's impossible. So at the time when I was doing my PhD, the dominant thought was that if you want to see one-dimensional signature of one-dimensional system, you have to have very small so-called split gate device to avoid disorder that would smear out the effect. On the other hand, I thought, well, the signal that I'm going to have from such a sub-micron size feature is going to be very small. So I would rather take an array of one-dimensional wires and look at the signal from this device. When I presented this concept to my supervisor, he said it will never work because of this disorder. But I thought, well, still I have to try. Luckily for me, the device worked. So I didn't have to spend another year or two working on a different device. And it was quite satisfactory to see it working. What was even more satisfactory was to see that this device concept that I established, both concept and fabrication, was used by students after me. If I remember correctly, someone even looked at the signature of Luttinger liquids using this apparently two disordered system to see one-dimensional wires.
Can I maybe ask a little bit? So for non-experts, so at the time these devices were done already with electron beam lithography, or?
Yes, they were done using electron beam lithography. We were doing our own electron beam lithography in converted SEM.
Yeah, at your time this was still much more exciting than it is for me today.
That's right. It was more exciting, but of course it was much closer to black magic than it is today. We had all our beliefs over what is going to work and what is not going to work. No one ever dared to go into systematically studying what's going to work because it was very time consuming. Well, our interest was, of course, in having a device to study exciting physics.
So indeed, for example, in my group, we still have one of these Wright Pioneer machines, which is an electron microscope, but a scanning electron microscope. But of course, today the machine can also be used for electron beam writing, but the software and everything to take a pattern that you draw in your computer and write it onto the machine is entirely automated by the company for the most part.
Yes.
So I guess at
the
time
we didn't have it.
You still needed to do electronic tricks to sort of.
No, we were extremely lucky in that, as we discussed, the difference between engineering and physics. In the group, we had very experienced people in programming. So we actually had home-written programs to direct the electron beam in the areas we wanted. And this really facilitated the research that we were doing. As you see, the cross-linking between engineering, electronic engineering, software engineering, physics, I have hard time to decouple them. I think somehow we need them all.
And I mean, also the Cavendish laboratory is not just any place in physics, right? It's forgot who's really famous. Is it Rutherford maybe? Who is it famous? I mean, Cavendish is also famous himself.
Cavendish, right? Yes. Well, there are quite a few famous people who went through the Cavendish. Cavendish, of course, changed location in physics. I think, from the more recent physicists that are famous was Sir Neville Mott and Brian Josephson, who I had the pleasure actually of having some seminars with. As in our first year of PhD, we were encouraged to attend series of seminars by professors in the Cavendish itself.
Yeah, Brian Josephson had a very successul PhD.
Indeed.
That much can be said.
Yes, indeed.
These kind of devices also require cryogenics, right? So during your PhD, you already worked with cryogenics. I think, wasn't Piotr Kapitsa at Cavendish?
Yes, he was indeed.
And he's
but
like
it was still the old Cavendish. We already were in the new so-called temporary building that after 50 or 60 years is finally going to...
But as we know, at RWTH Aachen, Jülich and Cologne, all buildings are temporary.
Yes, I think it must be a common theme for all physics departments.
So just back to the cryogenics question, sorry. I guess the cryogenics you worked with then were not so different from what we have today. It was just also a bit more
That's correct.
Handmade.
Yes, it's true that there is not much difference. My final experiments were performed in dilution refrigerators. I remember it was a fantastic workout. We didn't need any gyms. Inserting the probe, it was top-loading fridge, and the sample rod was rather heavy. I still remember practicing loading it. The other difference is that, again, I was probably the first generation of PhD students who benefited from having data acquisition program written by Professor Chris Ford that allowed me to run experiments, let's say, overnight without waking up every 2 hours to reset a parameter to carry on with experiments. But in this sense, we also did things a little bit more manual than we do now.
So yeah, in principle, your PhD was already the full sort of run of device physics as we practice it still today.
Indeed, it's true.
But So from your PhD in electronic devices, you eventually ended up going more into the directions of photons, right?
That is true as well.
So how did this happen?
When I was already finishing my PhD, it was about that time then the growth of indium arsenide and demonstration of the photonic properties has been demonstrated. And after, I still carried on transport measurement as a postdoc in Arizona and then Oxford. But then I joined Toshiba Research Lab in Cambridge. And the theme of the lab was quantum communication. The idea that I was employed to explore is the possibility of detecting single photons by photocharges trapped in quantum dots, as seen in transport through a narrow two-dimensional channel. So that, as you see, this change from transport to optical measurements happened gradually. And while in this lab, of course, there was also a work on single photon sources. And it became quite clear that quantum dots are objects that are ideally suited to serve as single photon sources, maybe not as much as single photon detectors. And I, since then, I really work on this on the interface between the two transport and optics fields.
All right, we will try to finish up a bit the career story and then talk more about your research. Just a few remarks still on the career. You have lived in 5 different countries and done research there at different places, and that's of course quite important to learn science from different ways of science and different viewpoints. How important do you think this moving around is?
5 countries might not be necessary, that's for sure. However, I think it's very important to stay dynamic in the way we think, and exposure to different style of working, exposure to different methods of solving problems, or even different methods of posing questions is always useful and interesting. And in this sense, I think it is very useful to be embedded and work for longer than 2 weeks in a different lab. Of course, what I would also say is very important is exposure to different culture. Science is very international. Sooner or later, some of those who stay longer become leaders who look after young people from different countries, and some understanding of cultural differences is always useful.
So you grew up in Poland and studied there. Then you went to England and then there's the US and Scandinavia and Germany, right?
Mm-hmm.
Or let's say, I guess like the difference from Poland to England is already quite big, right? In sort of the culture and
yes,
maybe among the contrasts, it seems like a very striking contrast.
Yes, it's true, but still, I think US is the biggest difference especially culturally or socially. Scientifically, Denmark was an interesting place, partly because it's a small nation of only 5 million people. And as you can imagine, the way funding works, the interactions between scientists work very differently from large countries where you are unlikely to know everyone doing an interesting science. So that's I would say are the biggest contrasts. Not only did I change countries, but I also changed. I was educated. I was brought up in still communist Poland, moved to hardcore capitalist US. So I've seen quite a few changes in my life. But I think I will reserve it for my memoirs when I retire.
Yeah, I think, I mean, it's true that there's certainly, I think, maybe a difference between the European way of science and the US way of science in terms of how application focused or how fundamental research focused we are, maybe. Or maybe in a way of selling it more. But at any rate, Americans are very good at finding good ways to sell science. Maybe more
that is very true. That the emphasis on selling is probably much more important in US than it is in Europe. Science is perhaps it's associated with how it is funded. Perhaps it is also that in Europe science probably was always a little bit on the pedestal of being something to look up to. Scientists, artists had a little bit different standing. I would say it's a longer tradition in Europe of science being part of a culture of a country, whereas in America, it's perhaps it was a little bit more a tool for economic growth. But I'm not sure that.
I mean, this has certainly the incentive structure maybe is different, but it certainly works in terms of producing results. I think we can probably still learn some things from the American research community.
I'm not sure if we can learn from the research or maybe from the innovation, so the transfer of research into applications. That's where we have to learn from them.
This is a bit good cue to maybe talk briefly about your time at Toshiba. So I think this is also very interesting for any listeners who are academics or from outside academia, because you have a perspective on both. How was the research in a company like Toshiba?
It was extremely fulfilling. It was very interesting. It's different in the sense that, of course, it was very much goal-oriented and structured. But that was the price we paid for being fully funded and not needing to spend the time to write grant proposals. There was a short report of our results by the end of year to justify further funding. And then we could spend the rest of the year really working in the lab and doing science. I'm not sure how representative these laboratories of industrial environment, because we did work with PhD students from the Cavendish laboratory. So it was not too dissimilar to conducting research here in the Forschungszentrum. The reporting was a little bit more, as I say, strategic, or rather the goals were more strategic. So it has its advantages for those who don't like writing grant proposals.
And do you think the company also, for a company like Toshiba, I mean, it's a larger scale company, so they don't need immediate returns, but eventually they want something that can be sold, right? How does this feel in the...
Well, the large corporations like Toshiba like to have flagship projects that serve a little bit like advertisement. And even though there was a specific goal of achieving QKD system that will be practical, and a goal that has been achieved, at the same time, this research laboratory was, and the collaboration with Toshiba was seen very much as showing that the company works also on the longer term projects. Large companies are not... The benefit of large corporations from small labs as Toshiba would be patents that would be grouped together and sold, exchanged together. And therefore, it might not feel so different to working in the academia, in the sense that even if you don't succeed to deliver a specific product, there will be, as long as there is innovation, that can be patented, it is of value for the company.
Was there more pressure to patent than here in Jülich?
Definitely, yes. But there was also much more support to do so.
Okay. Because, I think that for the German, or maybe even for the greater European science, there has been more, I think I've now more science friends who have patented some of their research. I think PhD students are getting more encouraged to do it.
Yes.
Than let's say 10 years ago even.
That is true.
But it's still, it's
Patenting
tricky. It costs a lot of money.
It costs a lot of money, and writing a successful patent is not a trivial task, because you have to be aware of phrasing your innovation in the way that cannot be easily overcome. And an input from patent agents teaching how to write is very important. It's a very different skill from writing proposals or writing papers. And therefore, as I said, support is really very important.
So your career basically led you to now being an expert on electronic devices and optics, which you here in your research at Jülich bring together, right? So
that is true.
The core of your research is bringing together electronics and optics, and
that is right.
And coupling, and material science plays a key role there. What's your materials? What are the material systems that you see as the key material systems for light matter interaction? Or is
it does seem that gallium arsenide-based heterostructures are extremely successful in light-matter interactions. The advantage, or maybe I start differently. Indium arsenide quantum dots became really a workhorse of semiconductor quantum optics. And I think it reached the maturity that we can use it in devices to create more complex photonic states. And that's where the current research is really in perfecting single photon sources or photon sources from indium arsenide quantum dots in order to employ them in quantum optics experiments. So I think this material will stay with us for some time. But as I say, it reached maturity of almost engineering problem. On the other hand, the discovery of photoluminescence from transition metal dichalcogenates caught attention of pretty much everyone who works with quantum optics, both in atomic systems and in semiconductor systems. At the moment, there is a lot of work on fundamental properties of these materials, and a bit on engineering. So I expect that we will hear a lot about new physics coming from this material system.
Okay, so maybe, let's try to cover a little bit of the basics in a way that people can understand. I don't know how, this is always a difficult part, but so to understand light matter interaction, so you have these photons and they come in, and then you have a semiconductor, but in reality there's usually this talk about like quantum dots and excitons. Why are these things, what is the way that the light and matter interact, and why is this material engineering there so important?
Mm-hmm. So semiconductors are the class of materials which have just the right band gap that you require a photon of specific energy to be able to excite an electron from the valence band to the conduction band. If you have bulk material, of course, you don't know where this photon is going to be absorbed. There is huge number of electrons in the valence band that can be excited into conduction band, and we all know that by doing so we generate We generate electricity with solar panels, or we have photon detectors. However, if you want to perform experiments on the quantum optics level, you need to isolate one quantum state. You need to isolate an electron that will be absorbing light in order to be able to convert the quantum information in the more deterministic way. This is why quantum dots. This is why quantum dots are used, because there you really limit number of electrons that are capable of absorbing a photon and creating excitation as a result.
And you also, this exciton is just right that you have some part of the semiconductor that gets excited by one photon, right? That's what we call an exciton.
Exciton is electron-hole pair that is bound by Coulomb interactions. If you take gallium arsenide at room temperature, you are simply creating electron-hole pairs. They are independent, they move through the crystal independently. And these Coulomb interactions that in gallium arsenide require lower temperatures mean that you form a quasi-particle of electron and hole. And
so this in this interaction of light and matter, somehow let's say this quantum dot, let's maybe first talk about the quantum dot. So the quantum dot is, for example, a different material, like you have this gallium arsenide and you have a little bit of a different material, for example, this indium arsenide, yes, where you have sort of an island, right?
You are very right that we should start from defining quantum dot. This is an object in which electron motion is restricted in all three directions. So three-dimensional quantum well, or I'm never sure if I should say 0 or 3.
Would you call like you can also just have a single atom in the gallium arsenide that is a donor?
Yes, you can.
And in principle, this donor is also sort of like a quantum dot, right?
It also is capable of trapping a single exciton. Yes, yeah. We wouldn't call it quantum dot, but it is capable of trapping single exciton, and therefore it could also serve as two-level system.
Which is why it's so important to make these materials perfect, right? Because somehow these out-of-place atoms or wrong atoms or play a very important role.
They do play a very important role. Most of the time, we have variety of methods to isolate photons. One of them, or isolate excitons. One of them is wavelength. That an object, if we come with a photon of specific wavelength, only some of the states can be excited. So in this sense, your donors or defects around quantum dot might not be so detrimental, but they can serve as an intermediate state which would absorb the energy after generation and then lead to, let's say, non-radiative recombination. So indeed, purity is very, very important. Isolation of this two-level system in such a way that the electron will remain there and you can do your state processing, quantum processing, and in there is very important.
So one of the reasons gallium arsenide is so good is because people have been perfecting it for a long time, right?
Yes. We have fantastic methods to grow very pure crystals. And the wonderful feature of this material system is that we have a continuum of band gaps between gallium arsenide and aluminium arsenide associated with crystals of the same crystal structure and lattice constant. What it means that you can grow any combination of gallium arsenide and aluminium gallium arsenide of any composition, layer by layer, without creating defects. So you can form quantum wells that will confine electrons, but you can also grow microcavities that trap photons. In one crystal structure where atoms sit exactly in their positions.
Yeah, that's right, because the refractive indices for the gallium arsenide and aluminum
are different. Yes,
are different. So you can use this to manipulate the light interaction.
Indeed.
So yeah, it is quite a unique material. It's a semiconductor, which means that you can put some metal on the back of it, and you can change the properties by putting a voltage. Right?
And you can introduce doping, so you can create p-n junctions to create, for example, light-emitting diodes or control the electrostatic environment. It is a very versatile material in this respect.
Is doping a blessing or a curse?
If it is remote, it's blessing. If it is near the object of interest, it can be curse.
Yeah, because it's kind of a very interesting problem is how to like in this material, you usually don't have necessarily free electrons, so you need to, especially when it's cold, so you need to put these dopants. But these dopant lands, like there's a very important question of how to sort of introduce doping, but without introducing noise from doping, right?
That is very true. The one way to do it is to use remote doping. So displace your electron gas from the layer where the dopants are. And a second rule is, this is why we use low temperature. Charges are frozen and don't necessarily, if structure is grown properly and we don't have additional defects, the charges are frozen at the sites of dopants which are not ionized and don't introduce much noise.
Okay, so let's maybe talk a bit about the applications. So the device that we want a device where you press a button and it emits a photon.
Those are devices that we have. What we want to do in our project is to combine the device that you described, a photon emitter, with quantum processor based on spin qubits realized also in gallium arsenide, but using gating, so qubits which can be electrically manipulated.
So essentially you want your single photon source to be able to talk to a more like another type of qubit in the same material.
That is right. And the reason to do that is the following. If we want to transfer information, photonic qubits, of course, are the medium of choice. They don't interact with matter very strongly, so they can be transported fair distance. But there is a limit to this distance. Information gets lost if we transfer information too far. And we need to, in classical telecommunication, you simply installed an amplifier that amplifies optical signal and send it further. No cloning theory tells us we cannot do it with quantum states. So we have to find another way, and the way to do it is to create a device called quantum repeater. These quantum repeaters are likely to be small quantum processors, for example, such as can be realized by spin qubits, which are arranged to interact with each other. So the role of this device is to make a connection between photonic qubit and ultimately quantum processor that would be able to read, purify the information and send it further.
So we have a qubit that wants to talk to another qubit through a photon, or?
So you can imagine that I want to send a qubit very far from beyond what the distance of direct transmission is, and I want to have this qubit absorbed in the quantum repeater, where the information will be read, conditioned, and sent further.
Is this like a completely reciprocal process? Like, is there a difference between, sending out the photon or catching it? Or do you think both of these processes are equally hard? Like you just need to get it to work
I will be able to answer it once we start making experiments. Both come with their own challenges.
Another really important challenge is you have your photon. You want, I guess, gallium arsenide is somewhere in the infrared, if I remember.
It is near
Which is
infrared.
not so bad, right? Because for telecommunication purposes, that's not such a bad wavelength.
It is not a very convenient wavelength for telecom for fiber communication. And gallium arsenide band gap lies at 800 nanometers. Quantum dots, depending on the size, are somewhere near 900 nanometers. The telecom preferred wavelength is 1550 nanometers.
So factor 2, roughly.
And we need to be able to convert the wavelength.
Would it be easier if it was exactly a factor 2?
No, it wouldn't make much difference. Perhaps it would even make it worse. However, the wavelength is not too bad for free optics communication, which is 850. Again, I'm not sure that we still might need to have wavelength conversion.
There's several engineering challenges there for sure. Like getting the photon from a fiber into the material. But that's maybe not the hardest part.
I think the harder part is getting a photon from the material into the fiber. Fibers are only a few micron in diameter. The mode of the photon is Gaussian. If you take bulk material like gallium arsenide, the emission goes in the entire sphere, and you collect very small fraction of all photons that are generated. So there are a lot of challenges to force the photons emitted by
we should maybe mention that classically this is very easy, because if you just want to communicate using light, you don't mind if you lose a certain fraction.
Indeed.
But as soon as if it is single photon, you really want to have like an 80% success rate or something.
Oh, you really want 100%.
I mean, of course, but I mean, 80% would already be pretty good. Or at least a lot of the experiments right now are running at maybe
a lot of experiments are run with efficiencies of even less than 80%. But if you look closely, every conclusion to a paper that uses a source with 80% efficiency will make a remark to we need better efficiency. Having said that, current fabrication techniques show that you can now get efficiencies in the 90s.
So your research is really at the point, an interaction point. So I think, does this the ML4Q cluster is about bringing different research groups together. So on the coupling with the quantum dot qubits, you work with Hendrik Blum, right?
That is correct.
And so how is the cluster helpful in facilitating these kinds of collaborations? Do you think that?
Yes, I think it is essential actually for the collaborations. What is very exciting as well, of course, on this particular device, I work with Hendrik Blum, who is an expert in spin qubits, and on the other hand, on the connection between the photon generated in this device and fiber, we collaborate with two groups. We collaborate with University in Bonn. There we have a lab full of experts in manipulating photons, and we work on wavelength conversion that you mentioned already. We also collaborate on methods to extract light efficiently without sacrificing the property of light. We also work with ILT in Aachen with also wavelength conversion, but for a different purpose. So the collaboration in Aachen is more related to sending photons through long links, 1550 nanometers, the telecom wavelength. The collaboration in Bonn, we want to achieve a connection between our quantum dots and ionic spin qubits, which are subject of research of Michael Coe.
Can I maybe ask, because we were now talking briefly about Bonn, like the quantum dots you can see as artificial atoms, right? But now there's also a lot of research into using real, there has been, a lot of the most impressive optical research early on was always done with real atoms, right?
Very true.
What do artificial atoms do better than real atoms, and what do they do worse?
What they do better. We have ability to tune wavelengths of emission to some degree. And you mentioned already semiconductors allow you to, for example, dope materials, which means that we can easily incorporate electrostatic manipulation of states. Not to mention that we can create integrated systems. For example, our mirrors can be incorporated in the same crystal. That means that devices are a little bit more stable, easier to manufacture. Once they are there, they are robust. What do we do worse? We are susceptible to noise from defects in the material. I think that is the biggest challenge, that we are susceptible to noise, which you don't necessarily have in vacuum.
On this experimental challenge, maybe just as a quick question also, how difficult is the challenge of bringing optics and cold temperatures together? Do you see this as how much of the challenge is cryogenics?
It's not a big problem, partly because typical experiments on pure optical systems require relatively high temperatures, which is just liquid helium temperature. The device we are working with, of course, needs the temperature dilution refrigerators, 100 millikelvin temperatures, because we need to operate the spin qubits. It becomes a little bit more challenging in the sense that the volume that you can cool down is perhaps a bit smaller, which means that we cannot put optical lenses to collect light very efficiently. However, it is not a fundamental problem. It has been realized in a variety of labs. The matter of cooling of the systems is solved.
All right, cool. Maybe I should ask at least one question about the monolayer semiconductors. These are the transition metal dichalcogenides,
yes,
which are stuff like tungsten diselenide or molybdenum diselenide. What are these? What makes this work? What's special about these systems? These are all pretty heavy elements, right?
They are very heavy elements. So you are very right. Spin-orbit interactions are extremely strong. But perhaps what is even more exciting for optics community is that they are true two-dimensional systems, which by definition increases the binding energy of excitons, so increases the excitonic effects by factor of 4. And on top of that, the electrostatic screening is very weak. We don't have the high dielectric constant of classic semiconductors, and that increases the Coulomb interactions between particles even further. So this is a very, very unique system to study many body effects. Complexes of 5 charges, 3 electrons, 2 holes have been observed. Of course, Bose-Einstein condensation becomes much easier to observe.
And these things are exfoliated, right? So it's a little bit like graphene or not?
It is very much like graphene. Most of the initial experiments have been done on exfoliated material.
For the non-experts, the Scotch tape method, right?
Scottish tape method, yes.
You take tape and you put it on the crystal.
Absolutely.
And you rip it off. And
absolutely.
You get a single atom layer.
Yes. In this case, three atomic layers, but very much the case. Of course, methods to grow them into layers are coming along very fast as well.
And wait, your work is also partially helped by the work of these 2 Japanese heroes who make this.
Yes. It's the boron nitride, the magic boron nitride.
Yeah, exactly. There's these two Japanese guys who are probably the most successful scientists of
Correct.
all time.
It seems to be the case that they are the only ones who produce high quality boron nitride, which doesn't have any charge traps and makes efficient cladding for our tungsten diselenide or molybdenum diselenide, which we mostly work on.
So you make a sandwich, basically.
This is a sandwich, yes. So, of course, the drawback of working with any two-dimensional material is that exposure to uncontrolled environment. So there is a lot of effort into making these sandwich structures with graphene as contacts, boron nitride as cladding, and two-dimensional material in our case, that semiconducting monolayers in the middle.
All right. Let's maybe do a brief intermission with rapid questions to go just over some quick, either or questions, maybe with short justifications. So I have to ask, because you worked in both Oxford or Cambridge, I guess you're Team Cambridge or
Team Cambridge.
Science or engineering, you also already answered, sort of.
Science, I think.
Academia or industry?
Academia.
Optical table or clean room?
Optical table.
And telecom wavelength or optical light?
Optical light.
All right. And then the gallium arsenide or tungsten diselenide?
Tough question. No answer.
Yeah, it's bad to answer. You have PhD students working on both, I guess, and you don't have to answer.
Even if I didn't, both, they are so different, you cannot compare.
Quantum optics or material science?
Quantum optics.
And BB84 or E91? I think it's
E91.
So you prefer the entanglement over the superposition, let's say, I guess.
Yes, I think it's more interesting.
For the non, these are just letters to the non-initiate, but to the quantum physicists, they are protocols of how to send keys, secret keys with quantum mechanics.
And it's the difference between single photons and entangled photon pairs.
Yeah. So we will just briefly now talk a bit about the future. Maybe just a few outlook questions. Do you believe that there will be a quantum internet for everyone?
I'm not sure what to answer. I would rather answer by posing a question: do we believe that everyone will need quantum internet? I feel that the vulnerability of internet as we know it is not in the data transfer at the moment. We hear all the news about hacking, and they usually come from hacking into stationary bits stored in computers rather than intercepting networks. And it is true that with quantum computers, our current coding methods will be vulnerable to attacks. But there is also the post-quantum codes, which are being developed by mathematicians. And perhaps those will be sufficient to make sure that networks are still not the most vulnerable place.
Yeah, you're probably right. I was going to also ask if the governments would allow secure communication between their people.
Well, my answer to that is a little provocative, and looking at recent battles of governments with high-tech companies makes me wonder if governments will have say in it, full stop.
Yeah, no, that is a good comment. That's true. And I mean, it's true that in principle, the type of cryptography that we have is pretty hard to hack. Although it did come out from time to time that there was known backdoors that maybe people at some secret agencies knew about early on.
Yes, but that is true. So my question was a bit provocative. Of course, I'm not saying that we are all sorted with security of networks, but I wouldn't say that data transfer is the most vulnerable part of the network.
Yeah, maybe I think a really key question in the quantum technologies that we are all working on. Do we have to eventually make physicists more engineering focused to make stuff that works and works reliably? Or do we have to teach just engineers how, do we have to work out the physics and then just teach engineers and then get the physicists out of there, because
No, I think we need both. But as might be apparent from everything we said today, I do not see that there is such a big gap as we are made to believe by having separate courses for engineers and for physicists.
And do you think this new master's program will help? Do you think that this type of educating a new generation to sort of think as quantum engineers, will this drive? Can we create?
Absolutely, I think it's a very good idea. What is exciting as well that we have this course run in parallel in the Department of Physics and Engineering. Again, I repeat, although we have this system of independent Department of Physics and Engineering, if you look at individual person, where their heart lies is always somewhere in between. And being exposed to two sides of the picture is the right approach.
As we have this now, let's say people sometimes talk about this Rhineland Silicon Valley, quantum Silicon Valley, or something like this, right? How important is it to have industry involvement at some level? Do you think that one part of the US success in the quantum technologies is that they have the semiconductor companies that are already ready to, or the companies like Toshiba in England to interface with research and catch it early. Do you need this to make this research?
It certainly helps. I would say it helps to have industry. Part of the reason is that for a concept to become a product, there is much more than simply showing that it operates. If you look at QKD, quantum key distribution systems, demonstrating that it's possible to send photons and code information on quantum in the quantum state was not enough to persuade users to adopt it. There was a very long path in creating, standardizing it, approving it, and convincing users that they will buy a product according to some standards, and therefore they will be able to expect some performance. And this is where I think we academics do not have the resources, we don't have the experience to do it. So we cannot quite specify what will be needed, and companies are much better in market research and understanding the needs and converting a concept into a product.
Yeah, maybe because I'm a little bit of a quantum optics nerd as well sometimes. Just I got to ask this question, but we're getting to the end, so it's fine if I ask some question. I mean, in superconducting circuits, which I work on, it's pretty easy to squeeze light, but maybe not necessarily. I mean, also people do single photon stuff in the gigahertz regime, and both of these things produce interesting quantum states.
Very true.
So there's sort of these two paths in quantum optics, which is to make non-classical light from single photons and to make non-classical light via this Kerr nonlinearity and squeezing. And in materials research, this is also quite interesting, right? Because you have very different material science approaches to both of them.
Very true, very true. You have, there are two competing technologies, or two competing, maybe not even competing. There are the two concepts that can be used to do interesting quantum optics. Both of them are challenging. Maybe not even on the, effectively it's always a material challenge. With squeezed states, you have to control phase of a photon, of a state very well. And that means that you have to control your environment very much. Even the smallest change of temperature will affect phase of a propagating pulse of light. And this is very challenging to achieve. Having said that, of course, the most convincing demonstration of quantum supremacy comes from
exactly
boson sampling of squeezed states. But this was extremely well-controlled environment. When it comes to single photons, the biggest problem is, of course, loss of photons as they propagate. But this...
Just to interject, you think loss is a bigger problem than making identical single photon sources? Or?
Not always identical photons are necessary. When they are necessary, yes, it is also challenging. But I think overall still, when we talk about communication, it's the photon loss that is the most limiting factor. Here, however, a concept of cluster states, which are entangled states of many photons, are proposed to overcome this problem. So both of these light sources should be still explored to find.
Yeah, we don't know yet
best
what will be the system that ultimately works. Well, then I think we're at a good point to stop. Thank you a lot for doing this podcast episode with us. It was a pleasure to learn about your career and research. Do you have anything that we didn't discuss that we should still have mentioned?
I think there is one thing that I should make clear. In your questions about quantum internet, I gave an answer which could imply that I don't believe in it, which is not true. So I should finish with one remark that I do believe that we need quantum internet, for example, for distributed quantum computing, and there will be a variety of very specialized and important applications where we need quantum internet.
Indeed, yeah. I think indeed, like the question whether individual people will need the quantum internet, indeed, that's a different question.
Yes, it's
from
a different
whether it will be
question.
useful for building a large-scale quantum.
So I do not want to leave you with an impression that we are wasting time by researching quantum internet, quite opposite.
No, indeed. So yes, the quantum internet will hopefully be the place where you listen to this podcast in 20 years. And with this, thank you. And
thank you as well.